Today we're going to be talking about solving exponential equations. These are not exponential equations. Generally speaking, with solving equations, you want to use inverses or inverse operations to try to isolate your variable. So for example, in this first one here, to cancel out minus, you do add. To cancel out times, you do divide. And in the next one, to cancel out addition, you do subtraction. Cancel out division, you do multiplication. Cancel out squared, you do square root. That's how you isolate your variable. Then it gets a little more complicated. You have one like sine of x, where you have to use inverse sine on both sides, and you get x equal 30. Now we know from our previous trig equation lesson that there are an infinite number of solutions to that. That's the first quadrant solution. And we also learned that some equations, it actually makes more sense not to use inverses if you have some sneaky way around it, like the zero product property in the case of this quadratic. For our first few exponential equations, we're actually going to have a sneaky little way to do it rather than go through inverses. When solving exponential equations, we're going to try to get the bases the same. You can see here that 16 is a power of 2, so we can rewrite this as 2 to the x minus 5 equal 2 to the fourth. And this is an exponential equation because there's a variable in the exponent. Now, since the bases are the same and the exponential expressions are said to be equal to each other, that must mean that the exponents are the same. So from here, we can say that must mean that x minus 5 is equal to 4, and adding 5 to both sides, x is equal to 9. Let's try this one, which is slightly more complicated here. We're going to use our rules of exponents here. Like bases, when multiplying, you have to add your exponent, so this becomes 3 to the 2x minus 5. This is 3 cubed, and square root is the same thing as raising to the 1/2 power. So again, we continue to simplify this right side, so now that becomes 3 to the 3/2 power. And now that our bases are the same, we can equate the exponents. So 2x minus 5 is equal to 3 over 2. 2x is equal to 13 halves, adding 5 to both sides. And finally, dividing both sides by 2, I get half of 13 halves, or x is equal to 13 fourths. All right, now have a look at this one. But sir, 11 can't be written as a power of 2. You are absolutely right. It cannot. Now we know this answer has got to be somewhere between 3 and 4, because 2 to the 3rd power is 8 and 2 to the 4th power is 16. So somewhere between 3 and 4, maybe a bit closer to 3. Okay, so now we're going to have to use inverses. So let me introduce you to logarithms. We are not going to delve deeply into logarithms in this course. We're just going to show you how to use them for solving equations. But you're going to use them quite a bit over the next couple of years. So what we have to do with this one is we have to take log base 2 of both sides. Log base 2 of both sides, like this. Because whatever you do to one side, you have to do to the other side. Now this is going to make the left side equal to x, because logs and exponentials are inverses of each other. And the right side is now going to say log base 2 of 11. So you've isolated x. Hooray, we've isolated our variable, but I don't really feel any better off than I did just a few minutes ago, because I still don't really know what log base 2 of 10 is. Some of you are going to have a calculator that can evaluate logs with different bases on it. If you do, congrats to you. If you don't, you're going to need to use a formula called the change of base formula. And what the change of base formula says, that log base b of a can be written as log base m of a over log base m of b. So the point is, we can change it to any base that we want. Now, all of our calculators have log base 10 of x on it, which is the common log. So common, in fact, that we don't even usually write the 10. That's the same thing as just log of x. When you see log of x, it means the base is always going to be 10. Now, so that means that this thing can also be written like this. Log of a over log of b, where the base is now 10 and can easily be found on our calculator. Sometimes it's going to be useful to have a base other than 10, a base of your choosing. But for our purposes, we're mostly going to be using 10 because it's on our calculator and it's going to help us solve these equations. So with that in mind, then the next step of my equation here becomes x is equal to log of 11 over log of 2. And now I can go to my calculator and ask it. And my calculator says that is approximately 3.46, somewhere in between 3 and 4, just like we were expecting. Okay, let's try another one. All right, we solved this using our inverse operations. We divide both sides by 5 to cancel out that times 5, and we get 3 to the x minus 4 is equal to 2.6. Okay, and then what we're going to do is we're going to take log base 3 of both sides. So log base 3 of 3 to the x minus 4 and log base 3 of 2.6. That cancels those 3's out and leaves me with an x minus 4. So now my equation is suddenly linear. And this I can use my change of base formula and write as log of 2.6, which I can find on my calculator, over log of 3, which I can also find on my calculator. Then I add 4 to both sides. I get log of 2.6 over log of 3 plus 4. And this is called calculator ready form. So I just plug it into my calculator now, and it's going to tell me just about 4.87. And as with all equations, you can always put your solution back into the original equation to check and see if you're right. It is probably worth noting that if you go back to the first problem we did today, we look at this and we rewrite this given the same base, 2 to the 4th, that essentially what we're doing, log base 2, we take log base 2 of both sides, and we get x minus 5 equal 4. Adding 5, we get x equal 9. That even though it seems to be a little sneaky method that we're using, we're actually using inverse operations. We're taking log base 2 of both sides of the equation to get us from an exponential equation down to a nice, easy linear equation. Okay. All right, that ought to do it, so go do some homework.